All right, so today we're going to tackle a word you hear all the time, correlation. It's this super powerful idea for finding connections in the world around us, in everything from medicine to the stock market. But what does it actually mean? So here's what we're going to do. First, we'll look at how to actually see these relationships with our own eyes. Then, we'll figure out how to read them. What's their direction, their strength? After that, we're going to boil it all down to a single number called the correlation coefficient. And then we'll finish with the big one, the golden rule. Why correlation is not causation.
Okay, first things first. If you have a whole bunch of numbers, how in the world can you see if there's a relationship hiding in there?
Well, the answer is a simple but really powerful tool called a scatter plot. Some people call it a scattergram. All it is a graph where you plot pairs of measurements, like, say, a person's height and their weight, that both come from the same single source.
See, every scatter plot has a story to tell, and it uses two axes to do it. On the bottom, the horizontal x-axis, that's where we put what we think is the cause, the independent variable. And on the side, the vertical y-axis, that's where we put the effect, the dependent variable we're watching to see if it changes. And if you're ever like me and you forget which is which, there's this awesome little trick from our source material. Just picture a capital Y. If you stretch its tail straight down, it makes a vertical line, just like the y-axis. It's so simple, but it totally works.
Okay, let's actually build one right now. Let's pretend we're asking, does having more diagnoses mean a patient takes more medications? We take patient 1, who has 1 diagnosis and 3 meds, and we put a dot on the graph. Then patient 2, patient 3, patient 4, and boom, a picture starts to form from the data. That's our scatter plot.
Okay, so we've got our picture. Now what? Well, now we have to learn how to read the story it's telling us, and that really comes down to two things, its direction and its strength.
First up is direction. In our example with the patients, as the number of diagnoses went up, the number of meds also tended to go up. That's what we call a positive correlation. The dots trend upwards, from left to right. And then you've got the opposite, a negative correlation. Think about it. The more nurses you have on a hospital shift, the fewer patient complaints you're likely to get. As one goes up, the other goes down. The line trends downwards.
But, sometimes there's just nothing there, no relationship at all. Like, does the number of visitors a patient gets have anything to do with how long they stay in the hospital? Probably not. You just get this random cloud of dots. There's no rhyme or reason to it. And that, my friends, is what we call no correlation.
All right, attribute number 2 is strength. And this is all about how tightly the dots are clustered together. If they're all packed in close, kind of hugging an imaginary line, that's a strong correlation. But if they're scattered all over the place far away from that line, then it's a weak one.
And this brings up a really, really important warning from the field. If you're looking at data from the real world, especially in biology or medicine, and you see a perfect straight line, something's probably wrong. The source material tells this great story about a statistician who found a perfect correlation between a person's body weight and the estimated weight of their liver. Turns out, the formula used to estimate the liver's weight actually had the person's total body weight in it.
So, saying something is strong and positive is great, right? But what if we could boil all of that down, the direction and the strength, into just one single powerful number? Well, turns out we can.
It's called the correlation coefficient, and we just call it R. And hey, if you need a way to remember that, just really lean into the word correlation. It's this one number that basically tells you the whole story of the relationship in a single glance.
So this number, R, it always lives on this scale from -1 to +1. That's it. -1 means a perfect, straight, downhill line. +1 is a perfect, straight, uphill line. And a 0, that means there's absolutely no linear relationship between the two things. None.
All right, time to get our hands dirty with some actual data. Here we've got 7 patients. We have their diastolic blood pressure, and we have the number of doctor's appointments they had last year. We've got a hunch that maybe higher blood pressure leads to more appointments. Let's see.
Okay, so the actual formula to calculate R, well, the source material calls it a big, hairy calculation. And honestly, that's not wrong. It involves a whole bunch of steps and multiplying and square roots. So, we're going to skip doing it by hand and let the computer handle it.
And after we punch all those numbers into a calculator or a computer, voila! The correlation coefficient R for this particular set of data is 0.949.
Okay, so we got a number. Big deal, right? What does 0.949 actually mean? Well, let's break it down.
First, it's positive. That means as blood pressure goes up, appointments tend to go up. Second, the number itself, 0.949, is super close to +1. So what's our conclusion? For this group of patients, there is a strong, positive correlation between their blood pressure and how many appointments they have.
Wow, a strong correlation? That feels like a huge discovery, right? But hold on. This leads us right now to probably the single most important lesson you will ever learn about statistics.
Let me ask you a question. It's a pretty famous one. Did you know that when ice cream sales go up, murder rates also go up? I mean, it's a strong positive correlation. So, does that mean your pint of Rocky Road is making you a public menace?
Of course not. The ice cream isn't causing anything. The real connection is being caused by something else, something hidden in the background. Statisticians have a great name for this. They call it a lurking variable.
So what's the real culprit here? It's that lurking variable. Good old-fashioned warm weather. Think about it. Summer arrives. More people are outside interacting, which, sadly, can lead to more conflicts and crime. At the exact same time, more people are outside buying ice cream to cool off. The summer heat is causing both things to happen, completely independently of each other. And this, right here, is the absolute heart of the matter. You can find these weird connections everywhere. One famous example is the price of onions in Bangladesh tracking the US stock market. It proves a vital point. Just because two things move together doesn't mean one is causing the other. There could always be a lurking variable.
So here's the bottom line. Finding a correlation is awesome. It's powerful. It's often the very first step toward a big discovery. But that's all it is, the first step. You now know how to see the relationship. Your real job, your next challenge, is to always ask why.